My name is Emma Tegling. I am a lecturer in automatic control at Lund University.
And my name is Richard Pates, and I am also a lecturer at the Department of Automatic Control.
We are right now standing in front of the Öresund Bridge, which is south of Malmö, which in turn is close to Lund University. When we look out over this place, we can see several aspects of things that relate to our research. We can see traffic, we can see trains. In the far distance, we can see wind farms. We can see this bridge that connects two countries, symbolizing large and interconnected systems.
What is a large-scale system? For me, at least, control is the theory of feedback and how we react to our environments, we react to what we see, and how we take responses to those observations. And this is as true for a small-scale system as a large-scale system. But when systems are large, there's lots of feedback. And so for me, large-scale systems is the interaction of many feedback loops.
Exactly, because our society is getting more and more interconnected. We're creating large systems. We can see the electric power system, telecommunications, traffic systems, everything, all systems are becoming large and complex. And it is those large and complex systems, we have these millions, possibly millions of feedback interconnections and decisions being made everywhere in the system. And it is that feedback that we are interested in.
Yeah, and the traffic's really kind of a good example because it's so familiar. So when you are in your car, driving your car, you are looking around and seeing where the other cars are and making adjustments to how you drive. So you're performing local feedback there, but it's not just you on the road. It's lots of other people on the road making these same decisions, and the way they make those decisions affects how you need to make yours.
And the way this becomes automatic control is when we start to formalize those decisions and analyze how are those decisions being made. Yeah. And of course, when we start talking about self-driving cars, that is not necessarily a research area of ours, but self-driving cars need to be on those roads making automated decisions. And our work has to do with understanding, well, what happens when with self-driving cars in large systems, when we have lots and lots and lots of cars, how will that interaction work? Will it be possible? Will it cause problems?
The interaction of many independent things using feedback while still affecting how everyone else is using feedback, it's pretty new. Yeah.
Exactly, and that is at the core of what we do at our department.
Yes.
So when systems become very, very large, it is not usually possible to have a central agent or a central entity making the decisions for the entire network. Decisions need to be made in a decentralized manner. When we're moving to a smart power network with lots of renewables, we're going to have lots and lots of wind farms and solar panels and small power plants replacing the old traditional generating sources. In such a system, we typically call it a distributed power network. Decisions and control cannot be made in a control room somewhere in one place in the country. The decisions have to be made automatically everywhere around the network.
If you want to have a network that changes very dynamically in terms of its user base, you need to shift to these decentralized protocols or decentralized ways of making decisions. For power systems, they're changing very, very fast, faster than they ever have. And from the control perspective, this is very interesting because the types of device, so like wind turbines, solar, they're very different. Wind turbines, they don't spin at a constant rate. And so you have to completely re-look at how you solve all of the control issues that arise in power systems.
So automatic control plays a role in analyzing social network because our mathematical tools that help us predict if a power system can remain stable, we can also turn that around and analyze the emerging phenomena in a social network, such as opinion polarization. Can we understand why that happens by explaining it through small-scale feedback interactions, by the way I react when I see a piece of news in the media. And this is, of course, a highly interdisciplinary effort, but the kind of mathematical frameworks that we use can actually be used quite successfully to predict and explain behaviors that emerge on large scales.
It's remarkable how pervasive this concept of feedback is.
I think automatic control and the research that we do is really targeting questions of sustainability all the time.
Solving the control problems is not going to solve climate change, but you're not going to solve climate change without also tackling the control and feedback and dynamical aspects.
A sustainable future requires us to work together with the systems that we build. They need to work together in a smart way to create a large and complex system of sustainable engineering.
Yeah.
We can answer questions like, are these systems robust to changes? Can they handle unexpected disturbances? That's actually cool. This can be a blooper.
Yeah.